Thanks for joining us for another installment of our Expand AI seminar series here at SDSU in conjunction with TILOS. Today we have Roberto Morabito from EURECOM. He's currently an assistant professor in the network systems group at EURECOM in France, and he's also a docent at the University of Helsinki in Finland. He's previously held research positions at the University of Helsinki, at Ericsson Research in Finland, and also at Princeton University as a postdoc. He received his PhD in networking technology from Aalto University in 2019, and his research focuses on network systems, edge computing, and distributed AI, with an emphasis on resource-aware AI lifecycle management and interoperability. So I'm happy to welcome Roberto. We spent some time together at Ericsson Research on some of these topics, so I'm excited to see what he's working on now.
Thank you so much. Thanks again for the invitation and for the opportunity. Indeed, somehow I'm still working. I have actually some reference to some stuff that were done during the Ericsson period. Today, I'm going to spend some time on talking about this work that we've been doing, which is somehow the intersection between edge AI and large language models. So before getting into this topic, I just wanted to emphasize the fact that, I've been working on edge computing for quite some time already. I was mentioning about edge computing already in my PhD thesis and in my PhD publication, so more than 10 years ago. And I've been kind of kept following the evolution of edge computing also when it turned basically into something that today we call edge AI. And the generative AI wave is also kind of hitting edge computing. Here, just a few examples of this is already perhaps outdated already, in the sense that it was some news and presentation and research papers screenshotted a couple of years ago or a year ago. Things have been evolving and kept evolving quite nicely. So together with my students and a bunch of collaborators, we start to work on trying to understand what are the different trade-offs when it comes to generative AI and edge computing. We are not jumping into the wave and just pretending that everything goes smooth, that it's all in with large language models of generative AI. But actually, as you can see, as you will see from the talk today, we are trying to understand what are the limitations as well in this area. Another reason why I wanted to still keep working on generative AI at the edge is because the traditional issue that we have been facing when it comes, for example, to energy efficiency and the massive amount of training and requirements for energy in training in the case of pre-generative AI, are nowadays still apply. There are some studies that demonstrate how the training of models like GPT-3, so we're talking about models of a couple of years ago, employed amount of energy equivalent to the yearly amount of energy consumed by the entire population of Denmark. So quite impressive. But the big shift that is happening now is that is not just the training that is impacting from the energy efficiency point of view, but it's also the inference phase. So if you think about the fact that we are involving in either in production, but even for daily use, as we used to use Google, this type of language models massively. This basically implies that also the inference part has a big impact from the energy consumption perspective. And that's why we start to believe and start to investigate whether moving some computation from the cloud to the edge could also bring some benefit in this respect. These are essentially the three main research areas that we are currently covering in this area. Again, I won't spend much time. The focus is going to be on this third item that you can see. So how do we maintain these systems on the long run, somehow affecting also the sustainability and the life cycle of this system. But I just very briefly would like to provide you some some overview about the activities that we are doing also in terms of feasibility and dependability. So the first aspect concern on essentially trying to answer the question, can we really run language models or generative AI application on constrained edge devices? So we have been investigating largely this aspect. We published this paper a couple of months ago. It's quite a long paper, over 30 pages. We want to really understand what is going to happen in the moment that we take devices like a Raspberry Pi or Jetson or in Nano, and we test, for example, different setup for the device, like a different CPU governor setup or GPU settings, etc., etc. What is going to happen in terms of the trade-off when it comes to the inference latency or this token throughput or the usability and cost implication. Again, the talk is not about this, but I just wanted to give you some insight on what you would find reading this paper. So obviously we spent some time on trying to analyze what is happening, for example, in terms of scalability when we execute a language model. For example, these results relate to the execution of a 3 billion parameter model on both devices with different setup. As you can see here, we have a different CPU settings in power save, performance, and on demand. The same for GPU-based execution. We also tested a different type of quantization for the models for trying to figure out what are the trade-offs, what are the gains in terms of efficiency if we rely on one model rather than another one. But also, what was interesting for us to understand was this sort of time series profiling. We know that this language model and generative application have different phases, lifecycle phases. You have this prefill phase, which is kind of a burst of computation, as you can see here on the bottom. And when we transfer, for example, our request to the language model, and then the generation phase. So all these different trade-offs are studied in this paper, also from the energy efficiency perspective. But the main kind of takeaway that we wanted to bring to the community was not just this kind of bulk numbers related to inference latency or throughput, but also what are the implications, for example, in terms of usability. So this is an example of what would happen if we would constantly execute a certain large language model task, not even extremely heavyweight. It was a very simple 100 token generation. What is happening if we have a battery-powered edge device? We would be able to cope with the constant execution of this type of workload. And we basically figure out that evaluating 9 or 10 different language models, varying from 0.5 billion parameters to 9 billion parameters, which is already quite a stress for devices like a Raspberry Pi. But well, essentially, we figured out that in the best case, we should be able to keep the battery alive for our device only up to 7 hours. In the worst case, just a couple hours. So the idea of getting this to perform this kind of extensive benchmarking was actually to try to understand from the usability and cost point of view what are the implications of generative AI models at the edge. So feel free to have a look at the study and to reach out if you have any question related to this. The other aspect that we are currently investigating, it's more like related to my background, which is on network system, and trying to understand what is happening in the moment that we are dealing with decentralized and distributed edge computing system, where we have multiple edge devices. And here, what is interesting to observe now is that things are evolving quite interestingly, in the sense that they are getting more and more complex if we compare to the pre-generative AI area. Just to give you an example, this is, when the on-device inference is not enough, we are always dealing with this kind of, and we, for example, rely on distributed execution we need to still deal with the resource scarcity, with the complex task, this device heterogeneity. I've been focusing quite a lot on distribution of workload execution in heterogeneous environment in the past, and I think this is quite interesting also in these evolving scenarios. And we start to think how this type of distributed environment will evolve in the future now that we have a much more complex and different application compared to traditional computer vision type of task. So this is pretty much the picture that we have nowadays. We have, for example, a bunch of edge-based agent or devices that are executing specific tasks. We envision the fact that perhaps if we are running locally generative AI models, it's not enough to keep them locally, because the quality, the objective quality of these devices is not as good as the one that we have in cloud. But perhaps if we introduce some sort of collaboration between the edge and the cloud, we can come up with some interesting insight. And basically, from the network point of view, what is happening is that traditionally what we had was this kind of setup where we have a multiple agent, and we typically talk about offloading of a AI task from one device to another, right? We have our networking between devices. We have the computational load, the real-time computational load of the device, and perhaps based on the task complexity, one device cannot cope with the local execution and offload to another one. This is somehow the picture when it comes to the pre-generative AI era. But if we look now at the generative AI type of application, things are getting much more complex, because what we can demand now to this agent, and again, I'm talking about resource constraint type of devices, like the one we are seeing here. We have been doing an extensive observability study. You can find a reference here also at the end of the presentation. You're dealing with not just a simple offloading between one device to another, but you can perhaps think about coordinating reasoning between devices. For example, one device is much more specialized on a certain topic and can provide a better outcome respect to specific request than another one, and then can come up with a stronger solution, much more useful if done in a coordinated way. Or we can offload from the semantic point of view, for example, the knowledge or the data available in one node are semantically closer to my needs. So I rely on an agent that it's likely to provide better outcome when processing the application. And still we have the typical computing and networking issue that we need to deal with, which are kind of sort of coming as a heritage from the previous type of study. So this is again a very brief overview about this type of work. I'm also quite interested about this aspect, also somehow very similar to things that we have been doing back in the days at Ericsson, and continuing perhaps on that track. And then I will start now talking about this other work that is kind of intersecting, as I mentioned, edge AI and large language models, and one specific application and of this type of intersection. So when I start to think about this sort of intersection between edge AI and large language models, obviously there were two things that immediately pop up into my mind. The first is that the edge AI lifecycle, I will dig further on this shortly, is rather different than traditional machine learning lifecycle, the one that we have into the cloud. I will get to this shortly. And then when it comes to large language models, for me, the most natural way to emphasize this intersection was to try to take advantage of the code generation capabilities of this model. So we start to wonder, can we try to combine these capabilities and come up with some interesting work here? There are obviously also some kind of less scientific motivation for this. I'm not interested in this, but the push also, if we think about the market growing in large language models and also in AGI, they are spiking exponentially as you can see. But the real reason also why I'm interested in this life cycle management aspect of edge AI and tiny machine learning, you might find it, or embedded AI or embedded machine learning, you name it, is also because back in the days at Ericsson, it was in 2018 or 2019, so quite a long time ago, together with a colleague in the team in Finland, we start to work on this concept of tiny machine learning as a service. I won't give you the details. It was just starting at very early stage with this idea of tiny machine learning, and now to handle the lifecycle management of devices and the machine learning that can run on very constrained devices such as microcontrollers. So it's not really an economical push why I'm interested in this topic, but it's actually kind of the result of interest in this topic that it's coming from the activities I did many years ago. So just to give a bit of background, very shortly, if we think about the traditional machine learning life cycle, we have this kind of very basic step. Let's think about cloud execution. We have data processing, model design and training, model deployment, and model serving. But when we move to the edge or the tiny machine learning, things are getting a bit more complex because we are basically dealing with this essential difference that compare the execution on a microprocessor-based device or a microcontroller. When we are dealing with microprocessor, of course, from the cost, power consumption, and engineering effort, we are, of course, a bit paying. But when it comes to code portability and compatibility, things are much easier. But when we move to microcontroller, so we are dealing with, for example, with C++ type of code, the portability of the code is much more difficult to be handled. And the typical life cycle, especially taking into account that we are talking about devices, especially in the case of microcontroller, that do not have an operating system, do not have they have a few kilobytes of RAM, very constrained type of devices. We need to perform additional life cycle stage that forces somehow the model to fit in this type of devices. It's not just you take your TensorFlow, PyTorch, you run it on your Raspberry Pi, period, right? But in the case of microcontroller, you need to convert the model to a specific format. You need to optimize it further with quantization, knowledge distillation, etc. And then actually writing the code that works well and it's readable to be executed on this type of environment. To be more precise, when thinking about the software, it's quite straightforward for us when dealing with this kind of processor to import our NumPy library or whatever you wish, right? But in the case of microcontroller, this doesn't happen, right? You don't have this kind of possibility. So this implies that, for example, if you have a TensorFlow model, you need to convert it to a TensorFlow Lite format, and then you need to beat the binary of the model, making sure that the code that is going to run the AI inference activate properly the different peripherals of the device, etc., in an environment which is much more difficult to be handled compared to Python type of execution. So starting from this kind of environment, the microcontroller in particular, we start to essentially see that we can't really rely on this expectation that code generation is write once and run everywhere, because we have this different type of lifecycle management that we need to deal with, and also we need to deal with the fact that in AI we have a different trade-off, right? We have the resource constraint, the device. We have as I mentioned, very tiny memory. Peripherals that need to be handled in quite not typical way if compared to traditional OS-based type of systems. We have platform heterogeneity. You need to different type of tool chain or architecture for the underlying system. The environment becomes quite tricky. And also, like from in terms of expertise, this is interesting because the tiny machine learning and embedded ML is kind of intersecting a bit of the IoT, a bit the data science, but also the embedded systems engineer. So it's not also easy from the skill perspective to come up with efficient solutions. So just to keep this in mind, embedded machine learning is not just a small machine learning, but it's an actual kind of co-design process that involves this different aspect. And our goal was essentially trying to understand can we then use large language models for trying to tackle this complexity, right? We have an environment which is extremely complex to be handled. We need knowledge of embedded system, data science, software tool chain, etc., etc. So can we rely on large language model for automating this lifecycle management? Meaning that in automated fashion, we are able to start from the data collection and data processing up to the inference execution on the device simply in automated fashion. Can we have this ambition? What are the different trade-offs? So this was the kind of incipit of our work. Started everything with a master thesis topic with one of my students, who is now a PhD student, and continuing working on this. And we decided at first to target the microcontroller type of devices in order to understand this kind of, to make a sort of stress test, respect the capabilities, code generation capabilities of the devices. And let me also clarify that this is not just, you will see shortly, out of the box code generation, but eventually turned out to be in the development of a complex middleware that takes in consideration quite many different constraints and aspects that relate to what I just mentioned earlier regarding the criticalities of handling edge AI lifecycle. This is essentially eventually the middleware system that we ended up to develop. We have a human in the loop at the beginning, where essentially you provide information, respect, for example, I'm using an Arduino with such capabilities, I have available a camera, or this kind of context information. I'm going to run an object detection, respect this type of data set, in this kind of a type of interaction. We build the system in such a way that we can interact with different type of large language models, so it's kind of compatible with different type of LLM API. But obviously the core is this sort of autopilot core engine, where we have a different aspect that are developed there. One big key aspect relates to the prompt that interact with the large language models, but also how we handle the errors that are generated by the code generated by the language model and then executed on the device. Obviously, we interact with the traditional Python libraries. So it's quite complex system that eventually has the main goal of interacting with the device. And eventually we started with the MCU Arduino type of device, but we were able to extend it to MPU type of devices like a Raspberry Pi. You will see shortly. And eventually what the outcome, the type of artifact that we have out of this middleware, starting from the human input, is that, for example, if you provide a data set, then the language model should be able to process the data set, so performing typical data engineering task. Then optimize and converting the model, choosing. Do you have a question?
Just a quick question.
Sure.
So your engine in Autopilot core engine is interacting with multiple LLMs?
Exactly.
So the LLMs are interacting with each other too, or
no?
Like
yes, it's only one-to-one, but actually you have a good point. I will mention shortly why this kind of view with possible interaction with multiple language model is actually interesting. I will be getting to this shortly. So the model optimizer and conversion, we perform, for example, quantization, and we convert the model to the suitable platform that we are dealing with, and then eventually the actual code that is going to be executed. Sorry, no. The actual code is going to be executed on the device that, for example, perform the object detection, object recognition, etc. So this is a high-level view of the system. The operational workflow, very shortly, essentially, that as I mentioned, we start from the raw data set, and in a automated fashion, we are able to get to the actual code that is executed on the device. Let me clarify that we have been focusing mostly on this kind of stages like data processing, model conversion, and sketch generation, which are kind of dynamic within kind of a system. The training, it's always some sort of a straightforward aspect, and you would do it offline. For example, the system is able to fetch models from this kind of model lakes, right, and then perform the conversion as it is, right. So it's not a kind of time sensitive respect this kind of operational workflow. And let me say, and you will see soon why we spend a lot of time to trying to fine tune and build the prompt in such a way that we would have good results from our middleware. There is a lot of hype and discussion about this prompt engineering. So we tested any kind of setup for the prompt. Eventually, what it's kind of becoming a sort of engineering subject, right? And eventually, what will happen is that we build the template in such a way that they are kind of following this. It's almost becoming a sort of de facto standard where you define the context, you have a task specific instruction, the error handling specific. You provide some sort of specification that relates, for example, to the type of hardware or sensor and software you are dealing with, and that varies, of course, based on the type of device that you are using, and then how eventually building the inference code that will run into the device. But this wasn't a trivial task to be accomplished. This is one of the first example. You're mentioning that you're an expert in edge AI, etc., etc. Then you have how the language model is supposed to respond, what's the objective, the actual task. There are different type of prompt, of course, because we have different type of not only because of the different type of life cycle stages, but this is kind of an abstraction of the prompt. We have the workflow that is basically built up of 4 different type of prompt. The first one is kind of defining the runtime pattern. As you can see, it kind of includes the right libraries that need to be used when dealing with a certain application. You perform the pre-processing, for example, encoding the tensors or the images that are coming as an input, the inference itself and the post-processing. Then you have the application type of specification, the type of application itself that you are going to run, whether it's an object detection or something else. And then the sketch code generation. Sketch is typically kind of a sort of naming that is typically used in the context of Arduino Sketch, right? But here we adopted it for horizontally for all the devices, just for the sake of simplicity. And here you then ask the language model and the entire orchestration system to build to generate your Arduino file that then will be shipped onto the device. And you enforce some restriction. This obviously depends on the type of application. Very important is also the error handling. So what what is happening in the moment that we get an error. So we try to compile our code and it doesn't work. So we provide some additional instructions in order to feedback and interact back with the language model. So eventually, this is the workflow. Very shortly, the user in the loop, the task type, device profile, and prompt adapter. So what you just saw. Then the autopilot to start to interact with a large language model and the different tool chains. If there is a successful compilation, then the sketch is compiled into the device. If we have an error, then we start to reiterate with the language model up to a maximum number of attempts. That in our case was 5, and then eventually either the compilation succeed or then the human should get back and have a look at what is happening there. But the final outcome is supposed to be this actual code that is running into the device with appropriate libraries and so on and so forth. So this is just a small demo. You can see here that we are trying to generate a sketch generation. We are, informing all the technical specification of the application. We start to invoke the large language model to generate the sketch code. Of course, we were also relying on a bunch of tools that would allow us to monitor, for example, the token consumption or the errors that we are getting from the language model. And what is happening is that we try to compile the first time the code generated, and we get some type of error. Then this error is refactored by the error handling prompt, prompted back to the language model. Here you will see specifically what type of error we are getting here, right? Host error. So we just take the most meaningful part of this. We don't, of course, provide back the entire trace, but we try to localize the origin of the error, and then we feed back to the language. In this case, the third compilation attempt was eventually successful, and things start to work. We were able to compile the sketch, and then this is shipped into the device. These are the evaluation scenarios and platform that we have been used. As I mentioned, we originally started with MCU type of device with Arduino, with an Arduino board running some fluid classification, and we tested data processing, model conversion, and Arduino sketch generation. So pretty much the entire life cycle. For the MPU, so CPU-based execution, or TPU, tensor processing. So this is a device from Google, which has this tensor processing unit. We only tested the sketch generation because the data processing and model conversion are essentially the same. So the only thing that changed in the life cycle is this sketch generation. And just to give you some reference, we evaluate the success rate, so the percentage of successful run among total runs. Of course, total runs in the interaction with the language model. So you have this 5 attempts. So and then we average to get the successful the success rate. Here, just the definition of token. I'm sure you know what I'm talking about, and then the execution time, that basically how long does it take for each of the subtasks. So from the termination signal minus the first prompting token, so that the first token prompted by the language model. And we tested these different language model from GPT 4o to smaller language model, also some model that is specifically targeted for code generation, like this Crien coder 32 billion, or also the Codestral 22 billion. And also we tested some reasoning model, but I don't have that in the slide, but I can anticipate that this was the less performing model, and at some point we just remove it from our experiments. And if we wanted to understand what are the different trade-offs, how long does it take to compile the entire pipeline, what's the success rate. And this is the case of of this was one of the first analysis that we did with GPT-4o, and you can notice that the task completion success was quite high for the data processing and model conversion, so above 90%. But the big bottleneck was the sketch generation. So using GPT-4o was the success rate was below the 40%. Nevertheless, I would say that the bright side of this result is that if we look also at the execution time, you ended up to have the entire pipeline deployed in less than 200 seconds. So if you think this from a system perspective, for example, in a smart city, I'm sure that in 5 years, smart sensors deployed in smart cities will be kind of handled by this sort of autopilot. This is quite nice. You know, in 200 seconds, you are able to process the data that are coming, convert the model, and ship things onto the device and start to run in field. So, of course, the success rate is not impeccable for sketch generation, but still, there are also some good trade-off if we look at these results. Then we start to wonder, okay, what is happening then if we look at the small language model, right? Or if we look at language models that are specifically tailored for code generation. And here you can see that the success rate, while still fairly good for data processing and model conversion, jumped down to only 3% in the case of the sketch generation. In the next slide, I have actually the results for all pretty much all the language model that we tested. I think, yeah, there is also DeepSeek, but you can see very clearly how the sketch generation was the biggest bottleneck for this type of middleware. And also, what was for us interesting to observe when we're thinking about this relation between time and token is that we have, of course, this area where you can notice that the lower number of token consumption kind of suggests a success rate, and this actually connects to what was mentioned earlier, that perhaps what we can have in the future is a type of system that in the moment that we start to observe that our middleware or system start to consume too many tokens, that implies that perhaps there is something ongoing that is not working well. And that could imply that, for example, we might rely on other language model, or we stop wasting resources and we ask the human in the loop to intervene, and so on and so forth. The other aspect that I wanted to, this is just, again, a different view for highlighting that the main bottleneck was indeed this sketch generation. And we did also some sort of cost analysis. Of course, the GPT-4o had a cost for the API, and also in terms of time. You know, you waste a lot of time if the execution goes wrong, and you can notice that this might, look trivial. It's just 26 cents dollar. But again, if we think on a hyperscale where you have multiple devices and things need to be read multiple times, this cost eventually it's not really negligible, right? So from the system point of view, this is cost analysis also quite important. One other aspect that I wanted to emphasize here is that we also know that in the language model, you can fine-tune a lot of parameters, and it has been proved that for code generation, it's recommended to set, for example, this temperature of the language model, or this top P, so what's like the probability that you choose for the token to be selected, right? If you select it to 0.1 temperature and top P to 0.8, you will likely get better results for the code generation. We did test these, and here you can see the results for the Raspberry Pi and Coral TPU. And first of all, you can notice that for the sketch generation, we are talking about Python type of code. In the moment that we are leaving the type of the Python the C or C++ execution, the success rate for the sketch generation jump quite drastically, right? We had 0% for all the small language model. Here, for example, we have for 14 billion parameters P4, 100%. no matter what, right? So the constraint of the programming language is quite strong here. It really affects. And also you can notice something very interesting. We were quite surprised to notice. Well, the parameters for some of the model, fine-tuning the parameters kind of bring some advantage, for other not. But what was interesting for us was that the performance of the TPU were actually better than the CPU. And we start to think like, this is somehow not obvious, right? You might wonder, okay, but the Raspberry Pi code is much more developed, the community is much bigger, so what's wrong there? And actually it appeared that for how the language models are built and this kind of intrinsic entropy that they have in the model, in the moment that you're transferring information and that you are specifying that we are going to use a TPU, kind of the search happening inside the language model is much narrow than what is happening in the case of CPU execution, where, for example, for interacting with a camera, you can use Python libraries, you can use OpenCV, you can use multiple things, right? So this was actually quite interesting results that we got. Then also we performed some sort of semantic fidelity of generated code. So there are a few of these semantic similarity applied for code. It's not really something that should be taken for granted, but we had a ground truth to compare. So we had a code, for example, in the Arduino GitHub and in the most the repository with the highest GitHub star for the case of the Raspberry Pi TPU, and we compared the code generated with this kind of sort of a ground truth. Typically, you are suggested that between 0.8 in terms of precision and 0.9, you kind of get from semantic point of view good feedback. So the code is semantically equivalent to the ground truth. But obviously, this doesn't imply that you won't face additional problem, right? Because things can be unpredictable. And just to give you an example, this is not our case, but I just took an image from the internet. One practical example is that the code compile is executed correctly, but for example, the bounding boxes are completely screwed in the code generated. So we do have a three kind of dimension when it comes to the code generation. First, does it compile? Second, it's kind of semantically aligned. But third, in practice, does it work as it's supposed to work when running inference on video streaming and things like that? So these are, of course, also affect accuracy quite much. And last but not least, we wanted to understand how much for the different models. We did some sort of ablation study related to the prompt. So meaning that if we remove the information from the prompt, if we kind of streamline the kind of instructions, does this affect the success rate? And this was actually the case. You can notice that the success rate was shrinking in some, this is for the case of ablation, was diminishing quite a lot, especially for the case of TPU. And this is actually consistent to this sort of entropy aspect that I mentioned earlier. In the moment that you remove some reference with respect to the environment that you are going to use, the success rate drastically reduce. So this was also quite interesting. What we did next, at some point we start to think, I'll try to, I'm almost done, actually, a few minutes. We start to, okay, we have thousands of execution and logs. We literally have 1,000 of logs. And we start to think, but why we don't just start to analyze these logs and try to see where the language model fails? Because actually, we start to observe interesting things when we start to notice a lot of false positive cases. So the code was compiling, but then it wasn't doing anything. For example, here on the left, I can share the slides, it's a bit blurry here. The code was compiling, but simply because it was empty. It was just, right? It was empty. There wasn't any inference logic, but it was semantically correct, but it was empty. There wasn't anything. or in this case, they were instructions that were overriding each other, right? So losing in efficiency. So again, compilable is different than correct. So we start to think, okay, let's go and have a look at the logs and let's try to systematically classify them in order to get an overview. But before providing the overview, I just want to mention this. I said earlier that the language model prompt, we spend a lot of time on the prompt. This is an example of 3 different sketch generation prompt template. The differences are really tiny. Here we have everything nested in a JSON file. Here the task is specified outside, and here we have the task and the steps outside the JSON. So these tiny differences, semantically completely equivalent, were affecting quite a lot the success rate and execution time of the models. So this was also quite interesting for us to observe that the prompt formatting was affecting drastically. You can notice difference, like the success rate dropping from 30% to 15%, and the consumption of token or execution time also accordingly. So this was also quite interesting for us to observe. And then we went to analyze these thousands of logs, and we built some sort of taxonomy. You will find a reference also on the paper. This was we tried to build, trying to have some sort of meta group, the errors that are perhaps linked to prompt, to execution, to code generation themselves, to the libraries in API, for example, the missing library, or to then embedded machine learning or embedded system in a TensorFlow itself. For example, you are not calling correctly the peripheral, the camera, or importing the right library, and so on and so forth. And what was interesting to see is that the distribution of these errors was also varying based on the different language models. These are the categories that you can find here. The distribution was different. And again, I get back to your comment, right? This is quite interesting because what we start to think and what we are trying to work now is that, okay, but then we can build a system that perhaps in the moment that we realize that we start to get the same type of error, perhaps we know that this GPT-4 is more, it's more likely that it's going to fail because of this type of error. Perhaps we need to reroute our request to another language model or to make them cooperate in order to face this particular issue. And here it comes.
Something like a mixture of experts, right?
Exactly, among different models. And here it comes, this kind of well, this is kind of a more general level about the lesson learned, right? Like how to add the guardrails in the system, the need of standardizing prompt and the way of decoding information. But then also what we are trying to investigate now is this kind of symbolic approaches for can we actually compute the probability that our request will fail given this specific prompt, this model, this context, etc., and how to act accordingly. And I think that this was my last slide. Here are the references. I went without, not much actually. So references about the work. Of course, a lot of work has been done, especially the first activities about some of the students, but my student Han, who just started a PhD, is the big responsible in the good or bad of this work that I presented today about the middleware and lifecycle. Thank you so much. That's it.
Okay. Yeah, I have a question. So I was thinking, it came up early, and then I think you partially answered it, but you noticed these challenges related to code generation specific to like maybe the hardware platform you're targeting, right?
Yes,
the CPU
yes.
versus CPU problem. I was thinking about, do you think there's a similar problem, or really I'm wondering, how do you think the level of abstraction in the code that you target would affect this? I'll give you an example. Tuning or deploying a model with a PyTorch library versus doing it in CUDA, right? This is extreme examples, but you can, and I think you mentioned here the difference between like a Raspberry Pi where you have Linux and Python libraries versus like an Arduino where you have no OS, right? And you're using maybe some C libraries. What do you think where do you think that you would address this kind of like opportunity or option to maybe have different like granularity of the deployment?
Yeah, this is actually interesting because, of course, we start to look at a lot of software engineering work, and there are many activities, for example, and many publications that show that one approach could be that you first ask the language model to write Python code, and then you ask to convert it to C or C++. That typically might reduce the errors. Or a piece of code, even better. Like you just take kind of a piece of the code and you perform this kind of. So that's one approach that I've been seeing in literature, but it's extremely complex, right? And again, these were simple application that we tested. It was an object detection and fruit recognition. That's it. But if you think about like the type of application you're dealing with, where you have a simultaneous localization and mapping, plus, for example, an object detection, or you might have object tracking, then things become very, very complex, and you have these different type of tools you're dealing with. So it's not easy. It's not,
so maybe a follow-up related. If I wanted to, let's say I had my own library that I wanted to swap out for what you're using, would that be quite straightforward in your framework? Like in that early stage, I remember you defined, would I just modify that early stage and then the downstream would be updated?
Yes.
Awesome.
Yeah, you have kind of anchors in the prompt, for example, that
cool. Yeah, I would just change one of these templates,
exactly.
right? Very cool.
Yeah.
Thanks.
Yes.
So over in the slides, you mentioned that you switch from C to Python.
Yes.
And so I was wondering, what were you measuring there? Because for C, you measure whether or not, like the failure rate for compilation, right? But like for Python,
it was also the success rate.
But like do you compile the Python code?
Yeah. I mean, it wasn't compiling; it was just the execution, the successful execution on the device, right? Yeah, that was the difference, of course. Like it was the Python does it run successfully it does what it's supposed to do. But of course, as I mentioned, we had these cases where the start to make the object detection work, but then you have the bounding boxes perhaps in a wrong position. So it's quite interesting. So that the correctness is not just it works, it compiled, or it can be executed, but it also relates to the quality of the code and then how it's built basically.
And another question. So thinking your prompt workflow, I saw that you somewhere mentioned that you instructed the LLM to, like, if you don't know what you should do, just bail out, right? Something like that. I wanna ask if, like, how many times did they actually bail out instead of like hallucinating some answers?
You mean, sorry, can you repeat the question?
Could you go to the
one of the
prompt workflow?
The what? Sorry.
Prompt workflow.
Yes.
Yeah. So yes.
It was the number of attempts, right?
The number 4 in sketch generation. If uncertain, sketch code generation number 4.
Here.
Yeah, if uncertain.
Yeah, these were like some restriction that in order to it's likely that eventually will lead to the failure, right? But instead of adding additional stuff, or if you guessing, for example, what kind of peripheral you have, if you specify that you have a camera, instead of just guessing what kind of camera, it's just better to get the error and then to fix it in the iteration with the
So
handler.
like what I'm wondering is like, did you observe that like LLM actually
Yeah,
escape?
especially if you in the case you don't fine tune the parameters, like you kind of let them being a bit more a bit more probabilistic, let's say, more inventive. Let's say that was the case.